In mathematics, a geometric progression, also known as a geometric sequence, for example, the sequence 2, 6, 18, 54, is a geometric progression with common ratio 3. Similarly 10, 5, 2.5, 1.25, is a geometric sequence with common ratio 1/2. Examples of a geometric sequence are powers rk of a fixed number I, such as 2k and 3k. The general form of a geometric sequence is where R0 is the common ratio and A is a scale factor, equal to the sequence's start value. Elementary properties. The nth term of a geometric sequence with initial value A and common ratio R is given by such a geometric sequence also follows the recursive relation for every integer generally. To check whether a given sequence is geometric, one simply checks whether successive entries in the sequence all have the same ratio. The common ratio of a geometric sequence may be negative, resulting in an alternating sequence, with numbers switching from positive to negative and back. For instance 1, -3, 9, -27, 81, -243, is a geometric sequence with common ratio -3. The behavior of a geometric sequence depends on the value of the common ratio. If the common ratio is positive, the terms will all be the same sign as the initial term. Negative, the terms will alternate between positive and negative. Greater than 1, there will be exponential growth towards positive or negative infinity. 1. The progression is a constant sequence. Between -1 and 1 but not 0, there will be exponential decay towards 0. -1. The progression is an alternating sequence. Less than -1. For the absolute values there is exponential growth towards infinity, due to the alternating sign. Geometric sequences show exponential growth or exponential decay, as opposed to the linear growth of an arithmetic progression such as 4, 15, 26, 37, 48. This result was taken by T.R. Malthus as the mathematical foundation of his principle of population. Note that the two kinds of progression are related. Exponentiating each term of an arithmetic progression yields a geometric progression, while taking the logarithm of each term in a geometric progression with a positive common ratio yields an arithmetic progression. An interesting result of the definition of a geometric progression is that for any value of the common ratio, any three consecutive terms A, B and C will satisfy the following equation, where B is considered to be the geometric mean between A and C. Geometric series. A geometric series is the sum of the numbers in a geometric progression. For example, letting A be the first term, M be the number of terms, and R be the constant that each term is multiplied by to get the next term. The sum is given by. In the example above, this gives. The formula works for any real numbers A in R. For example, derivation. To derive this formula, first write a general geometric series as. We can find a simpler formula for this sum by multiplying both sides of the above equation by 1 minus R, and we'll see that since all the other terms cancel, if R1, we can rearrange the above to get the convenient formula for a geometric series that computes the sum of n terms. Related formulas: if one were to begin the sum not from k equals 0, but from a different value, say m, then differentiating this formula with respect to r allows us to arrive at formulae for sums of the form. For example, for a geometric series containing only even powers of r, multiply by 1 minus r2. Then equivalently, take r2 as the common ratio and use the standard formulation. For a series with only odd powers of r, an infinite geometric series. An infinite geometric series is an infinite series whose successive terms have a common ratio. Such a series converges if and only if the absolute value of the common ratio is less than 1. Its value can then be computed from the finite sum formulae since. Then, for a series containing only even powers of, and for odd powers only, in cases where the sum does not start at k equals 0, The formulae given above are valid only for r less than 1. The latter formula is valid in every Banach algebra, as long as the norm of r is less than 1, and also in the field of p-adic numbers if r p less than 1. As in the case for a finite sum, we can differentiate to calculate formulae for related sums. For example, this formula only works for r less than 1 as well. From this, it follows that, for r less than 1, also, the infinite series 1/2 plus 1/4 plus 1/8 plus 1/16 plus is an elementary example of a series that converges absolutely. It is a geometric series whose first term is 1/2 and whose common ratio is 1/2. So its sum is the inverse of the above series is 1/2 minus 1/4 plus 1/8 minus 1/16 plus is a simple example of an alternating series that converges absolutely. It is a geometric series whose first term is 1/2 and whose common ratio is minus 1/2. So its sum is complex numbers. The summation formula for geometric series remains valid even when the common ratio is a complex number. In this case, the condition that the absolute value of r be less than 1 becomes that the modulus of r be less than 1. It is possible to calculate the sums of some non-obvious geometric series. For example, consider the proposition. The proof of this comes from the fact that which is a consequence of Euler's formula. Substituting this into the original series gives. This is the difference of two geometric series, and so it is a straightforward application of the formula for infinite geometric series that completes the proof. Product. The product of a geometric progression is the product of all terms. If all terms are positive, then it can be quickly computed by taking the geometric mean of the progression's first and last term, and raising that mean to the power given by the number of terms. Proof. Let the product be represented by p. Now, carrying out the multiplications, we conclude that, applying the sum of arithmetic series, the expression will yield. We raise both sides to the second power, consequently, and, which concludes the proof. Relationship to geometry and Euclid's work. Books 8 and IX of Euclid's Elements analyzes geometric progressions and gives several of their properties.